Hey everyone, I'm recording this recitation again because I messed up the Wednesday 9 a.m. recitation and I'm not going to be here on Friday. So I'm just going to re-record, I guess, everything that I did on Wednesday, and then there'll be a few extra things at the end because I do have time to talk about it now that I didn't, I guess, in recitation, and since I don't have to pause for anything today, I can just essentially talk about whatever the heck I want in this allotted time. So let me move my mic real quick. Okay, so hopefully the sound is good. I don't want to mess up the sound again like I did in recitation. And so let's begin. So on Wednesday, I talked about ODEs and I talked about an ODE toolbox. And essentially, what we did is we solved we consider the initial value problem, and I didn't actually do initial value problem in class, so I'll do one here at the end. So we have the differential equation y nth derivative of t plus a1t times y to the n minus 1 derivative of t plus all the way down to a n t y of t is equal to f of t. Okay, so this is the differential equation given to us, and then we're going to be given some initial value conditions, which are the nth minus 1 derivative at some point t naught, and that's going to be some constant c1, and then the nth minus second derivative at that point t naught is going to be some other constant, and then all the way down to y t naught is equal to some constant cn. Okay, and then so what does all of this mean? In this case, a1 through an and f are continuous functions, and c1 through cn are given constants. All right, so these constants c1 through cn will be given in the problem. These guys here, these are called initial value initial values, all right, or the initial conditions. Probably initial conditions is the word that we want there. Okay, so now what? Okay, so we have this differential equation, and we often rewrite this part of the differential equation as the following. So we often rewrite as the following. So we use the derivative operator instead, which is d to the n plus alpha 1 or a1 d to the n minus 1 plus a2 d to the n minus 2, right, plus dot 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 plus an applied to y is equal to f of t. Okay, and so now what is this? So these guys here, instead of writing the derivative, we use the notation of the derivative map instead. Okay, and so the derivative map is d from c1i to c0i, so continuous functions that are one-time differentiable, and then they become one-time less differentiable. That's what d does, is the derivative map. And so what it does is d of y is equal to y prime. Okay, so you can see that d to the n of y is going to be y n primes. Okay, and then L is the linear operator. So this guy in purple, all these d's in the brackets, that's called L. And so this equation here, we sometimes write as Ly is equal to F. And then N is the order of the ODE. And in this class, we usually deal with second order ODEs, but N can be any number that we want it to be. It has to be an integer, of course. And okay, f of t is the right-hand side function. All right, so if f of t is equal to 0, then it's homogeneous. If f of t is not equal to 0, it's non-homogeneous. All right, and so in particular today, we'll just be dealing with the homogeneous case. So this is on the midterm. But the non-homogeneous case, it will not be on the midterm. Again, let me just make sure I'm actually recording. It looks like it. Okay, cool. So, okay, so f of t is the right-hand side function. So now what? So now let's talk about y. Y of t is called the general solution. Okay, y of t is the general solution, and it's composed of two parts. The first part is going to be the homogeneous solution. So y of t is equal to yh of t plus yp of t. All right, so this has a lot. This is analogous to ax equals b, where x, right, is really the solutions. X of t, or x here, is equal to the homogeneous x. So any vector in the kernel, this is any vector in the kernel plus the particular solution to ax equals b. Because if you shift that particular solution by the kernel, well, the kernel solves ax equals 0, so you're really not adding anything to b. So this is the exact same idea. Yh is the solution to the homogeneous diffie-q. So, okay, so yh equals the solution to the homogeneous diffie-q. So this is a basis for the kernel of L, right? Because we're solving here, up here, Ly is equal to f. And so when we're solving the homogeneous system, right, the homogeneous system is really Ly is equal to 0. And so any solution to this homogeneous system is in the kernel of the derivative operator L, or the linear operator L. Okay, so yh is a solution to the homogeneous diffie-q. It's actually a linear combination of a basis. So actually, that's it's a linear combination of basis elements for the kernel of L. So that's the way you want to think about it. Okay, and then y of p is the particular solution to the non-homogeneous diffie-q. All right, so you have two parts to it. You have the homogeneous and you have the non-homogeneous part, and combined together, you'll make y of t, which is the general solution. All right, so now what we're going to do is the following. We're just going to do a bunch of examples, and hopefully we can learn from the examples. So all of these are determine the general solution to the diffie-q. And so all of these are going to be homogeneous. The first one is going to be y double prime plus 3y prime plus 2y is equal to 0. Okay, now, so what's the first step? The first step, if you recall to this diffie-q, when we wrote it up here, was we wanted to rewrite that diffie-q in terms of the derivative operator. And so that's what I'm going to do right now. Right, so remember, y double prime is essentially the derivative operator applied to y twice. So that's going to be d squared. And then 3 times y prime, that's 3 times the derivative operator applied to y. So that's, well, 3dy, but let's not keep it that for now. So 3d, and then plus 2, and then all of this is applied to y. Okay, so you can think of distributing the y through, and that's going to be equal to 0. So that's how we write it with the derivative operator. Okay, the next step is to rewrite all of this again. So it seems like a pain to do so because we're seemingly just rewriting the equation for no reason, but we're going to write it in terms of the in terms of the auxiliary polynomial. So r squared plus 3r plus 2. So we just substitute the d's into r's, and then the reason we do this is because we let y equal e to the rt. Okay, and so now this is e to the rt. This y just got replaced by e to the rt. And the reason we let that is because when we consider the derivative of e to the rt, so d dt of e to the rt, it's r e to the rt, right? So the important thing about the exponential function e is that when you take the derivative, the original base part just stays, and then there are like constants that fall out of it, and noticeably this r. And so we adjust for these constants falling out with these like constants instead. So that's why we're comfortable with letting e to the rt be our guess for y. And so this is going to be always the case. All right, so we rewrite it now as r squared plus 3r plus 2 times e to the rt is equal to 0. And now the solution, or the roots to this polynomial, are going to be the solutions of r that we want. So once we factor it, we get r plus 1, r plus 2 times e to the rt is equal to 0. Right, and what can solve this? Well, only r equals -1 and -2 solves it, because this function is always, the e function is always greater than 0, right? It's never exactly 0. So the only way that this entire thing can be 0 is if either this first term or the second term is 0. Okay, so what did this mean? Okay, so this means then, so e to the rt is in the kernel of L, and so now we want to find a kernel of L. In our case, the kernel of L is going to be the span of e to the -1t, so e to the -t, and e to the -2t. Right, so we found our r's, and now we just plug them into e to the rt, okay, and then that's going to be what our kernel is. All right, and then finally, y of t is equal to yh plus yp, okay. The homogeneous solution here is, remember, a linear combination of the kernel vectors. So that's what I want to say. So the linear combination of a basis for kernel of L. So here we have a basis for kernel of L, and so linear combination is c1 e to the -t plus c2 e to the -t. And then yp, well, yp solves the particular solution on the right-hand side, right? So we want to plug in something for y that makes this 0 on the right-hand side. And if we let y equal 0, that solves the particular solution, because if you're taking derivatives of 0, you're just going to get 0. And so, yeah, and that's always going to be the case. This is always the case for the homogeneous ODEs that we're dealing with right now. Okay, so really what happens is then y of t is equal to y of h, so that's going to be c1 e to the -t plus c2 e to the -t. All right, so yt is equal to the homogeneous solution for the homogeneous ODE, and that makes sense, because why would we call them homogeneous ODEs if the homogeneous solution didn't solve them? Okay, so that's one example. So here's another example. Y double prime minus 3y minus 10y is equal to 0. So now we get d squared minus 3d minus 10y is equal to 0. Okay, and so now let's actually do something different. Actually, no, we'll do something different at the end. Actually, I'm going to save this example for the end. So now let's take a look at another example. Y double prime plus 14y prime plus 49y is equal to 0. Okay, and now what? So now this is d squared plus 14d plus 49 applied to y is equal to 0, and then we rewrite it in terms of r, right? 14r plus 49 e to the rt is equal to 0. Okay, so these first steps right here are the exact same first three steps that we did in the previous one. Right, we have our diffie q, we write it in terms of the linear operator times y, and now we write it in terms of the auxiliary polynomial. So I forgot to write that in. Auxiliary polynomial. This thing is also the auxiliary polynomial. All right, times e to the rt is equal to 0. And now when we factor the auxiliary polynomial, we get r plus 7 squared, e to the rt is equal to 0. Okay, so r is equal to -7 twice, so this has a multiplicity of 2, right? It's a repeated root in our case. And so when we want to write the kernel, right? The kernel of L, well, now we get the following is equal to the span of e to the -7t, e to the -7t. Okay? But this is a little problematic, because what is the dimension of the kernel of L? Well, L is a second degree linear operator, right? So remember, n is the order, so a second order linear operator. So that's what L is. And so L should really have 2 dimensions. Okay, so it should be 2-dimensional because we have a second order ODE. So the problem here is that this is not 2-dimensional. right? These two are the same thing. These are linearly dependent. And so right now the kernel is one-dimensional. So how can we make the kernel two-dimensional? And here is where the first kind of trick appears. What we need to do is that whenever you see linearly dependent elements in your kernel, just add a t or powers of t in front of them. Okay? So in this case, e to the negative 7t and t to the negative 7t are going to be in my kernel, and so then my my solution y of t, remember, is just the homogeneous solution again, is going to be c1 e to the negative 7t plus c2 t e to the negative 7t. Okay, and in general, let's check that e to the negative that t e to the negative 7t is in the kernel of L, right? So what do? I legit just plug in t to the negative 7t into y. Okay, so what I do is I let y equal t e to the negative 7t, and then so now what happens? Well, remember I plug it in for y, but there's a y prime and a y double prime term, right? So their derivatives are you have to take the derivatives. So now y prime is equal to, using the product rule, e to the negative 7t minus 7t e to the negative 7t. Okay, I'm going to rewrite this as 1 minus 7t times e to the negative 7t. All right, so we're using the derivative, the product rule here, and then now what? Y double prime is going to be equal to, so now you take the derivative of this guy, and so use the product rule again. You can say that's equal to negative 7 e to the negative 7t plus 1 minus 7t times negative 7, and then e to the negative 7t, right? And so combining these terms, this is a positive 49t, and then this is a minus 7t, so we get negative 14 plus 49t e to the negative 7t. All right, so that's just algebra. Know how to take your product rules. Okay, so now what? So now remember, I have y double prime plus 14y prime plus 49y is equal to 0. So I want to show that this is, in fact, what works. So now, okay, y double prime is equal to, right, that guy. This is negative 14 plus 49t e to the negative 7t, and then plus 14 times, so that's y double prime, and then 14 times y prime, which is the second term, which was up here, right? 14 times 1 minus 7t e to the negative 7t, and then plus 49 times t e to the negative 7t, which was what we plugged in for y. Okay, so this is y double prime, and then there's y. Okay, so we want to see if this is equal to 0 or not, and yeah, it should equal 0. So if you work this out, you get negative 14, so you get negative 14 here, and then you get a plus 14 e to the negative 7t, right? So here you get a negative 14, here you get a positive 14 e to the 7t, so they cancel out. Okay, so like this guy kills this guy, and then now you're left with a 49, so this is a 49t. Here, 14 times negative 7 is a negative 98t, and then plus here, this is a positive 49t, and so they cancel out, and so what you end up getting is you end up getting 0 is equal to 0. So yeah, so t to the negative 17 works in general, and if you had even more repetitions, so let's say I had another e to the 7t, just hypothetically, not for this problem, right, then I would need to add another power, so that would be t squared e to the negative 7t, and you just keep on adding these powers. All right, we're talking about the general solution to problems like these at the end. All right, third equation is the following. So, okay, let me have my notes up. So now let's talk about y double prime plus 2y prime plus 5y is equal to 0. Okay, and now we get d squared plus 2d plus 5 applied to y is equal to 0. And rewriting it with the auxiliary polynomial, right, r squared plus 2r plus 5, and then this should be e to the rt is equal to 0. So r is equal to -2 plus or minus root 4 minus 20. So you can't factor that polynomial. You have to use quadratic formula. And you'll see that we get -1 plus or minus 2i. Okay, so we have complex roots. And what do we do in the following? So right now, kernel of L is equal to the span of e to the -1 plus 2i times t and e to the -1 plus 2i minus 2i times t, right? Because there are two roots here. One of them is the plus and one of them is the minus. So, okay, now, all right, we have that. That's the span. But one thing we don't like is that our differential equation up here has no imaginary terms. And now, all of a sudden, our kernel, right, has I terms inside. So what we do is that we want to get rid of the I terms. And I did a derivation in Recitation, but I'm not going to do it here just to save time. If you really want to, you can look at your notes again. I don't think you don't need to know the derivation in class. So what we do instead is the following. This right here is of the form a plus bi, or a plus or minus bi, right? So your roots are a plus or minus bi, and so in this case, a is equal to -1 and b is equal to 2, okay? So now what? Now the kernel of L is also equal to the span of e to the at cosine bt, comma, e to the at sine bt, all right? And so for those of you in Recitation, on Friday Recitation, I'm not going to derive why this is the case. You can either ask Wednesday kids why this is the case, how I derived it. Again, not important. But if you plug these guys into the equation, right? If you plug, so in our case, that's the span of e to the -t cosine 2t, comma, e to the -t sine 2t, right? If you plug these equations in for y up here, it's going to work, all right? So it just works that way, and the derivation is not too tricky. But to prove that it works, you just do the same thing that we did for t e to the -7t here. You just let y equal one of these guys and take derivatives. Okay? So then, so y of t is going to be equal to c1 e to the -t cosine 2t plus c2 e to the -t sine 2t. Okay, and now what? So now let's combine all of this together, and let's say I have this example. So example 4, let's say it's like d plus 5 cubed plus d plus 5 cubed times d squared plus 4 minus 4d plus 8 squared, y is equal to 0. Okay, so we already gave it to you in this linear operator form. So this is really, right, r plus 5 cubed, r squared minus 4r plus 8 squared e to the rt is equal to 0. So what are my roots? My roots are r is equal to -5 with multiplicity 3. And then r is equal to 4 plus or minus root 16 minus 32 all over 2. So that's 2 plus or minus 2i. So my roots are equal to -5 mult 3 and 2 plus or minus 2i. But remember, 2 plus or minus 2i is just the root for this guy, but we're squaring it as well. All right, so this is 2 plus or 2i, 2 plus or minus 2i multiplicity 2. So each one of these roots in the plus or minus has multiplicity 2. Okay, so 2 plus 2i is repeated twice, and 2 minus 2i is repeated twice, and that's because of that square term on top of that guy. Okay, so how do we do this? What's the kernel of L? Well, the kernel of L is equal to the span of, so we write down e to the -5t, e to the -5t, e to the -5t, and then we realize, okay, so now we need our t and we need our t squared in front of these guys to make them linearly independent from e to the -5t. Okay, and the same thing happens here. So we have, so e to the at, e to the 2t, cosine 2t, e to the 2t sine 2t. But remember, these get repeated. So now I got e to the 2t cosine 2t, e to the 2t sine 2t. And then for these repeated terms, you just add an t in front like usual. All right, so that's that's the fourth example, and that should cover pretty much every example that you have of ODEs that you need to be able to solve. Okay, so I've been talking about linear independence a little bit, and so how do we show that equations are linearly independent, or solutions to ODEs are linearly independent? And so let's talk about linear independence of solutions to ODEs. Okay, and so the way we do this is by using the Wronskian. And there's a difference between the chapter 4 Wronskian and the chapter 8 Wronskian, which is the ODEs that we're talking about now. All right, so chapter 8 Wronskians are for ODEs, and chapter 4 Wronskians, actually, we'll save that for later. Okay, so what do we do? Well, how do you calculate the Wronskian? If you remember, W of y1 through yn, y2 through yn, at some point t is equal to the determinant, right? So these are determinant brackets of, let's say, y1, right, of t, y2 of t, yn of t. And remember, you just keep on taking derivatives until you have a square matrix. So this is y1 prime, y1 double prime, all the way down to y1 n minus 1th derivative. Okay, that's what makes this square, y2 prime, y2 double prime, right? y2 to the n minus 1th derivative, and then over here, this is yn to the n minus 1th derivative. Okay, so remember, you take the determinant of this matrix, okay? And in chapter 4, right, this checks the linear independence of any function, any set of functions. All right, and how did we determine linear independence? Well, if you remember, if w equals 0 for all t, remember what happens? Nothing, absolutely nothing happens, right? We couldn't make, this test was inconclusive if w equaled 0 for every t. So no matter what t we plugged into the Wronskian and took the determinant, it doesn't matter if it were 0 because it doesn't tell us anything. So, but if w was not equal to 0 at any t, then the set was linearly independent, right? So if we could find any t that made this determinant non-zero, we knew that all the functions in that set, y1 through yn, right, are linearly independent if the determinant was not 0 anywhere. So how does that differ from the chapter 8 Wronskian? Well, the way you calculate this is the exact same. Okay, so you still calculate the exact same thing, except now these y1s through yns, they're going to be solutions to your ODEs, right? So this, now we check for lin independence of solutions to the homogeneous ODE, essentially Ly is equal to 0, right? And remember, L is the derivative operator up here. Right, so up here, we talked about how the homogeneous was Ly equal to 0. Okay, so we check for the linear independence of solutions to the homogeneous ODE, Ly equal to 0. So now here's where stuff differs. All right, if W equals 0 at any t, then it's linearly dependent. All right, contrast that with what it was before. And then if W was not equal to 0 everywhere, so every t, right, then you get linearly independent. Okay, so notice the difference between the chapter 4 Wronskian when you just plug in any random functions and the chapter 8 Wronskian where you plug in solutions to the homogeneous ODE. You need to be careful about about the interpretation of the Wronskian. Okay, so now let's talk about some general remarks. Right? If distinct roots, right? So there are many ways to see ODEs, and we saw 3 cases above, and so these are the cases just summarized. So if you have distinct roots R1, R2, right, all the way through Rn, then your kernel of L is going to be the span of e to the R1t, e to the R2t, all the way to e to the Rnt, and then y of t is going to be C1 e to the R1t plus C2 e to the R2t plus all the way to Cn e to the Rnt. Right, so that's if each root is distinct. Okay, if you have a repeated root, and let's say R, right, and let's say it's repeated n times, then the kernel of L is equal to the span of e to the RT, t e to the RT, t squared e to the RT, all the way over to t to the n minus 1 e to the RT. And remember, this has to be n minus 1 because you need to have n terms in here. Okay? And so here you don't have a t term, so that's why this ends up being n minus 1. Okay? And now what? So y of t is going to be C1 e to the RT plus C2 t e to the RT plus C3 t squared e to the RT plus dot 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 all the way up to Cn t to the n minus 1 e to the RT. All right, number 3 is the last one. If complex roots r equals a plus or minus bi. Right, and remember, a can be negative, but b cannot be negative. All right, so b we kind of just read it off, and a we take whatever sign is in front of a as well. So, so a is any real number, and b kind of has to be greater than or equal to 0. Right, we just read off what the b value is, and then for a we have to take into account what sign is there. So kernel of L is equal to the span of e to the at cosine bt e to the at sine bt, right, is the span of these guys, and then so y of t is equal to C1 e to the at cosine bt plus C2 e to the at sine bt. Okay, so here's where I stopped in recitation. And because I do have a little more time now, I can talk about a few other things. So let's talk about initial value conditions. So the initial value problem. Okay, so in recitation I did this other ODE, which was y double prime minus 3y minus 3y prime minus 10y is equal to 0. Okay, I'm just going to make sure all my other derivatives are correct. Yeah, they look fine. Okay, so yeah, let's say I have this ODE. But now, remember, so I give you this ODE, but what also can I do? I can give you initial conditions, right, starting with the n minus 1th derivative, right? So if I have y squared, right, plus something y plus ay prime plus by, right, I can start giving conditions on y prime, and I can give conditions on y, right, because they're the n minus 1th and below terms. So let's do that. So let's say I had y prime at 0 is equal to, I don't know, what should we make it? Y prime at 0, so let's say y prime of 0 is equal to 2, and let's say y of 0 is equal to 1. Okay, so how do I solve this diffie-q? Well, step 1 is to solve the homogeneous just in general. So this is d squared minus 3d minus 10 applied to y is equal to 0. R squared minus 3r plus minus 10 e to the rt is equal to 0. This is r minus 5, r plus 2, e to the rt is equal to 0. So r is equal to 5 and negative 2. So kernel of L is equal to the span of e to the 5t, e to the negative 2t, and then y of t is equal to c1 e to the 5t plus c2 e to the negative 2t. Okay, so we've solved the homogeneous. So now what do? Well, we have these unknown coefficients, all right? And so the initial values, right, initial conditions help us find for the unknown constants. All right, so the initial conditions help us solve for the unknown constants. And so here, right, we don't know what C1 and C2 are, but we know what y prime is 0 and we know what y of 0 is. So y of 0 is equal to C1 times e to the 5 times 0 plus C2 e to the 5 negative 2 times 0. Well, that's equal to C1 times 1, because this is e to the 0, plus C2 times 1. All right? And what is this? Well, we know that this is also equal to 0, right? Because, or 1, sorry. We know that y of 0 is equal to 1, and so now we know that C1 plus C2 is equal to 1 for my initial conditions. All right, so now we have to do the same thing. We know y prime at 0. So now, so this is step 2. Right, is to find the unknowns. Let me use a different color. So find the unknown constants. Right, that's step 2. So what do we do now? So we know y of 0. So now we need to find y prime at t, right? Because we need to find we need to find y prime at 0 eventually. So I have y of t here. And now I just need to start taking derivatives, right? And so I get 5c1 e to the 5t plus negative 2c2 e to the minus 2t, right? And just like before, you need to be careful of the product rule if you have the product rule, okay? So here, these guys are easy to take derivatives of, but in general, it might not be. You might have a messy product rule derivative. Okay, so this is really a minus sign here, right? So this is really minus 2c2 e to the negative 2t. And so now we know what y prime of 0 is. That's 5c1 minus 2c2. And we know that that was equal to 2. All right, so now I have my other equation, 5c1 minus 2c2 is equal to 2. And so, okay, so how are we going to solve this? Well, this is a system of 2 equations, 2 unknowns. And we can solve it simply by, row reducing it, making substitutions. And so we should get like 7c1 is equal to 4. So c1 is equal to 4/7, and the c2 is equal to 3/7 as well. Okay, so this is, so I did row 1, or 2 row 1 plus row 2 is how I got this guy. Right, 2 row 1 plus row 2 is equal to 7c1 is equal to 4, and then here you go, you get your constants. So now we know what y of t actually is. To solve these initial value conditions, we know that it's going to be 4/7 e to the 5t plus 3/7 e to the negative 2t. Right, so we just plug these constants into the initial equation, and this is going to be my final answer. Okay, so we actually done this on the homework a little bit and before. So if you look at some of your previous homework problems, you've actually had to solve some problems with initial value conditions. Okay, last thing I'm going to talk about is then system of equations. All right, and so this is essentially an extension of what Professor McGrath did in lecture, and specifically we're be talking about Jordan form systems. All right, so since we can talk about it in Jordan form, you can apply it to non-Jordan form as well, and I actually encourage you to do it on the homework. So on the recitation homework, you have an example, a question like this, and in your normal homework, you had an example where you didn't have Jordan form, but here you're going to have Jordan form. So let's just see a little bit of how you do these types of problems with the methods that we have currently. Okay, so essentially, let's solve x prime of t is equal to 6x of t plus or minus 8y of t, and then y prime of t is equal to 2x of t minus 2y of t. Okay, and so now what? Well, we can want to write this in vector notation. So this is x prime y prime is equal to 6, 2, negative 8, negative 2. Sorry, I'm reading off the columns. And then this is times xy, right? And so this is our system of equations. And really what we have here is x. So I'll call it this vector z is equal to some matrix A times z. All right, in the book, they're going to call this x prime is equal to ax. Yeah, so let's just, so let's just leave it like this. This is a vector x. Note that this is a vector x is equal to x prime, y prime, not just like the function x of t. All right, so that's what x is equal to. So we write x prime is equal to ax. All right, so now what do we do? Well, we want to make a change of basis, okay? Because this system right here isn't solvable immediately. And so what we're going to do is we're going to make a change of basis. And we're going to let x prime, not x, but we're going to let the vector x, all right, because this is x prime vector, this is the x vector. So we're going to let that vector x equal some s times some vector v. Okay? And then v, the vector v, is going to be equal to x tilde y tilde. Okay? So now what? So we know that x is equal to sv. So if we actually plug that in here, this is going to be sv prime is equal to a times sv, right? We just replaced the x equals sv, right? And we just replace that in for x there, and that's how we get this guy down here. All right, but what do we notice? Well, we notice then that this becomes v prime is equal to s inverse asv. And the reason is because you multiply this side by s inverse and you multiply this side by s inverse, and so that's how you get that. All right, so what is s inverse as? Well, we know that for a smart change of coordinates, right, s inverse as is going to be equal to the Jordan block of that matrix, right? Because j is equal to a is equal to sj s inverse, right? And so if we choose a smart enough s inverse as, that's just multiplying all these s's on the correct side to get them over on the other side, right? We're going to get s inverse as is equal to j. So for a smart s matrix, we get that. So what do we want to do now? So really, this is equal to v prime is equal to jv for a smart choice of the S matrix. All right, so what is a smart choice of the S matrix? Well, we literally just find the Jordan canonical form, find what Sj S inverse is, find the S matrix there, and we're just going to use that S matrix. All right, so now the step here is to find the JCF of A. Okay, so A was equal to, right, this matrix in the middle up here, x prime is equal to ax, so that's the 6, negative 8, 2, negative 2 matrix, and then so determinant of A minus lambda I ends up being 6 minus lambda minus 8, 2, negative 2 minus lambda, so this is lambda squared minus 4 lambda minus 12 plus 16, right? So that's lambda squared minus 4 lambda plus 4 is equal to 0. This is lambda minus 2 squared equal to 0. Lambda is equal to 2. All right, with multiplicity 2. All right, so now A minus 2i, right, is the following. A minus 2i for lambda equals 2 is 4, negative 8, 2, negative 4. Okay, and then now what? Well, this has rank 1 and nullity 1. So remember what we do now. Well, this is defective because this is multiplicity 2, and so this is less than 2, so it's defective. I remember what we do when we find defective matrices. Well, we find our J matrix, which is 2, 2, and there's going to be one block associated with with the 2 in the J block, and since there's only one way to split up a 2 by 2 block, we know this has to be 1 up there. Okay, so that's the J matrix, and then now for our S matrix, right, we need to find a cycle of generalized eigenvectors, where this is going to be some V, and then now this is going to be A minus lambda I times V, right? And so, okay, so now we need to find S. Right, and remember, so this entire block corresponds to a 2 cycle. So remember how we find cycles. So find S. So for our 2 cycle, right, A minus lambda I squared times V has to equal 0, but A minus lambda I times V cannot equal 0. So what is A minus lambda I squared? Well, A minus lambda I squared, well, here's A minus lambda I, which is A minus 2I, is equal to, what was it? 4, negative 8, 2, negative 4, right? And then A minus 2I squared is actually the 0 matrix. So I'm going to pick then, I'm going to pick my generalized eigenvector V to be 1, 0, okay? And then if I multiply that here, I'll get 4, 2. So when we go back up here, this is A minus 2I times V, right? And this is my V. So I can just replace this with 1, 0. And I can replace this with 4, 2. Okay, so my S matrix is going to be 4, 2, 1, 0. I actually don't know why I erased this. Let's just write those back in. So this is V, and this is A minus lambda I times V for a 2 cycle. Okay, so yeah, so I have my S matrix now, and what do I do from there? So recall from above, right? We have V prime is equal to JV, right? So so now that we found the S matrix, now that we find our Jordan form, recall that V prime is equal to JV, and that X is equal to SV. Right? So that's how we derive all of this. That's why we're even finding the Jordan form. And so now, right, V prime, what was V prime? V prime was equal to X tilde Y tilde, and X was equal to X prime Y prime. X vector is equal to X prime Y prime. So this is all the information we need. And so now we use V prime is equal to JV, and that's X tilde prime, Y tilde prime is equal, V is equal to X tilde, Y tilde, and X is equal to X of T, Y of T. All right, so this is what we have. Okay, so now V prime is X tilde, Y tilde prime is equal to J, which was 2, 2, 1 that we found above, times X tilde, Y tilde. Right? So that's what we did up here. So yeah, so that's the J that we found up here. And then now what? So now, right, if we break this out again, this is really, the first row is really X tilde prime is equal to 2X tilde plus Y tilde. And then the bottom row is Y tilde prime is equal to 2Y tilde. So that's just multiplying everything out. We can solve this diff EQ. Y tilde is equal to 2, Y tilde prime is equal to 2Y tilde, right? It's separable. So if you divide both sides, you'll get Y tilde prime over Y tilde is equal to 2. And then if you integrate both sides, you get ln of Y tilde is equal to 2t plus some constant c, and then y tilde then is equal to some constant times e to the 2t, right? So that's That's y tilde. All right, so now we know y tilde. We can plug that in for x tilde. So now x tilde is equal to 2x tilde plus c e to the 2t. Okay, and the way we solve this guy is by using the integrating factor. So now we get x tilde minus 2x tilde is equal to c1 e to the 2t, or yeah, let's call this c1. All right, so c1, this is c1 e to the 2t. Integrating factor, right, we move everything over, so now we have x tilde prime minus 2x tilde is equal to c1 e to the 2t. The integrating factor is e to the negative 2t, e to the integral of negative 2, right, dt, which is equal to e to the negative 2t. So multiply entire thing through by e to the negative 2t, and I'll get x tilde prime e to the negative 2t. Well, let's just do it this way. E to the negative 2t, x tilde prime minus 2x tilde is equal to c1, and then e to the 2t times e to the negative 2t is actually 1, right? It's e to the 0, so that's just c1. Okay, what's the left-hand side? The left-hand side, recall, is the derivative, then this becomes the derivative of x times e to the negative 2t, right? It's the derivative of x tilde times whatever the integrating factor is, and then that's equal to c1. Integrate both sides, x tilde is equal to e, x tilde times e to the negative 2t is equal to c1 t plus c2. And then what else? You get x tilde is equal to c1 t e to the 2t plus c2 e to the 2t. So that's x tilde. All right, so now what do we have? We have x tilde y tilde is equal to c1t e to the 2t plus c2 e to the 2t. Right, so that's the first entry, and the second entry, remember, was c1 e to the 2t, which was y tilde. All right, we're almost done. So the last step is we want to find x, right? And recall x is equal to s times v. So now, right, this is v. So now x is equal to s times v, and so x is equal to 4210, which was s, times c1t e to the 2t plus c2 e to the 2t, c1 e to the 2t. Okay, and then if we multiply this out, we'll get 4c1t e to the 2t plus 4c2 e to the 2t, and then plus c1 e to the 2t. And then on the bottom, we'll get 2c1t e to the 2t plus 2c2 e to the 2t. And so that's x, and that's actually the solution. And so the way we actually want to write this is break out the c1 and c2s. So this is really c1 e to the 2t, 1 plus 4t, 2t, plus c2 e to the 2t times 4 and 2. Okay, so that's just algebra going from this vector to this vector. They're the same thing. Okay, so that's it. I think that's everything I want to talk about in recitation. So again, some new stuff at the end. You're going to need to know how to do this because on your homework there was one example where instead of being J, it was a diagonal matrix, but the idea is the exact same, where you need to pick a smart choice of S, and then you'll get like V prime is equal to DV instead of JV. But the idea is the exact same thing. So you need to do this on recitation homework. It was on your previous homework, and you also need to know how to do this initial value problem stuff, which I also didn't get to in recitation. So again, sorry about the recording being really bad yesterday. It happens. It happened last semester as well. And I'll see you guys on, I guess, over the weekend for review sessions. Again, I'm not going to be there on Friday. I'm going to be away. So see you guys then.